Aloha everybody, this is Gigi from Kauai Community College. In this video, we'll be differentiating and integrating power series. So let's get started here. Okay, so let's start with our favorite power series, the geometric series. We know that within the interval of convergence from -1 to 1, not including the endpoints, that this geometric series converges to the function f of x is equal to 1 over 1 minus x, right? So now within that radius of convergence, we are going to go ahead and differentiate the function and then differentiate the polynomial or the series and see what happened. So f prime of x is going to be -1 over 1 minus x to the second power, right? Now, differentiating the polynomial part, we will have 1 plus 2x plus 3x and so on. And if this is going to be x to the fourth, then you'll have 4x to the third next, right? So again, we could only do this within this interval of convergence because that's when the series actually converges to this function here, meaning this is the series representation of this function within this interval of convergence. So you can only differentiate within that interval. Okay, now so we can write this function, this new function that we have here. Okay, that's the new function here. Okay, and that would be -1 over 1 minus x to the second power is going to equal to this series that we just came up with, right? So the thing to note is that you can only differentiate within that interval of convergence. So there's no guarantee what will happen with this newly differentiated series at the endpoints, meaning, okay, so we said it is going to converge from -1 to 1, not including the endpoints at the beginning, right? So what happened at the endpoints here? Well, when we do plug in 1 and -1 at the endpoints, you will see that you will get divergent series. So the interval of convergence here is going to remain the same. Now, does it always remain the same? No, you do have to check the endpoints. Okay, now the theorem that is proven said that you can only take the derivative within that interval of convergence, and then you do have to check the endpoints. And one thing that you will notice here is you may see that if we did just take the derivative of this the way it is, then shouldn't we get x to the k minus 1 with the k in front? Why is it here that I wrote k plus 1 to the k power? Well, because this original series starts at 0. Right? But if we did start at 0, it really doesn't make sense. You will have 0 multiplied by x to the -1 power to start with, which is not the pattern that we have. Or when x is 1, we will have, right? So it's just how you see this this series here. Okay, now how you observe that pattern, right? So I like to just go ahead and if I was to write this part right here, then I would write that would start at 1. That would start at 1 if I am writing k to times x to the k minus 1. So when you differentiate, you need directly from the series representation, you need to make sure that the index works out, okay? I like to just go ahead and look at the polynomial the long way, take the derivative, and then write down what I see. And that just makes more sense in my head, but up to you. All right. So again, we are going to start with this same geometric series. And this geometric series is going to converge to f of x when x is in between -1 and 1, not including the endpoints. That's your interval of convergence. Okay, what are we going to do this time? We are going to integrate the function. So when we do integrate the function f of x, we will have negative ln of the absolute value of 1 minus x, right? So the negative comes from this inside derivative right here being -1, okay? And you should be able to see that now. Okay, now we are going to go ahead and integrate this series representation in the polynomial looking part there. Then we will have x squared over 2, x to the third over 3, x to the fourth over 4, and so on, plus c, right? So wait a minute, a series doesn't have a c, so how do we reconcile the c? Well, let's think about this for a second. We know that since x is in between -1 and 1, then 1 minus x is going to be a positive number. So really, we no longer need the absolute value, right? And then also, when x is 0, you will have ln, negative ln of 1 on the left-hand side, and on the right-hand side, you will just have c, because all of these are 0, right? So you can reconcile the fact that c is equal to 0. Okay, c right here is equal to 0. So we can now go ahead and ignore the absolute value, and we can go ahead and say c is 0 based on that analysis right there. Okay, again, we can integrate within the interval of convergence, meaning only in between -1 and 1. So what happened at the endpoints? We really don't know. We have to go and check, right? So when x is -1, the series that we have is negative, and that would be -1 to the k power over k, and that is an alternating harmonic series. And alternating harmonic series converges, right? However, when x is 1, what are we going to get? We're going to have the negative in the front, 1 to infinity, and then we'll have 1 over k. 1 over k is the harmonic series, and the harmonic series diverges. So the interval of convergence for our newly obtained function when we are integrating, that interval of convergence is going to include -1 but not include 1. Okay, so again, when we are differentiating or integrating, we are doing that within the original interval of convergence, and then we do have to check the endpoints for the new series that we have just obtained. Okay. Now, this question I think is kind of fun. When I first saw this, I was like, how do you even go from inverse tangent to a polynomial? How does that even work? Well, one thing that we should remember is that the derivative of inverse tangent is 1 over 1 plus x squared, right? So what that means is inverse tangent is the integral of 1 over 1 plus x squared. And you have seen in the previous lesson that the function 1 over 1 plus x squared is the alternating even powers. And we obtain that within the radius of convergence of the geometric series when your x, your blank, is negative x squared, right? So we've seen that before. Now what we can do is go ahead and integrate that series, and I'm going to do that using the polynomial expanded form so that we can see the pattern a little bit better. Okay, so when we do that, and of course we will do that within the interval of convergence from -1 to 1, not including the endpoints. So we have inverse tangent is going to be now the odd power, right? The alternating odd power divided by that odd number, right? Now we do have to reconcile the c, right? So how do we do that? Again, when x is equal to 0, when you're balancing out the left-hand side and the right-hand side, you will see that c is equal to 0. Okay. Now again, the interval of convergence that we started out with is going to be in between -1 and 1, not including the endpoints. So we want to say what happened to this newly obtained series when we are at the endpoint. Okay, and if you go ahead, I didn't show my work here, but checking at the endpoints, we'll see that both of them will be converging, and you can use the alternating series test for those to say that both of those are going to converge. Therefore, the new series will have interval of convergence including the endpoints, -1 to 1. And that is what this theorem says in your book, right? It looks really complicated, but what it is saying is that you can go ahead and differentiate, and just like you normally would with any polynomial. And you notice here the theorem doesn't have the index there because you might have to re-index the series after you differentiate to make sure that the pattern works. And of course, that's why I always just write down the expanded form and differentiate the polynomial, and that would be easier to look at that way. And don't forget, after you differentiate or integrate, check the endpoints, because there's no guarantee that the newly obtained series will behave the same way as the original radius of convergence, like this right here, right? So you do have to check the endpoints after you integrate or differentiate. And that is it. That is what we are dealing with in terms of power series. Basically, we can combine them like how we did in the previous lesson. We can differentiate, we can integrate, and the reason why we can do all this is, as you know, these things look like polynomials, and polynomial functions are pretty awesome functions that you have learned in Calc 1, where you can do a lot of things with them, right? Because it's continuous and differentiable. And those are very important properties. So up next, you will see Taylor series. We'll define Taylor series, and we'll be working with Taylor series and the special type of Taylor series called Maclaurin series. So that would be the next video.